Good morning, students. So today we'll be discussing about the atomic structure starting from the Rutherford's model. As you know, everything around, including us, are matters, and we often wonder that what are these matters made of? Great human minds, curious human minds, has sought the answer of this question from ancient period. Rishi Kanad in 6th century BC said that everything around us are composed of very tiny particles which cannot be divided further, and he called these tiny particles as paramanus. And I hope you can still remember the Dalton's proposition about the atomic structure what he made in 1803 AD. In this line, in 1897, J.J. Thomson, through his experiment, could find out that any matter is at least made of some negatively charged particles, what he called as electrons. But as you know, as a whole, the atoms are electrically neutral, so there must be some positive charges which will compensate the negative charges of the electron. So, taking all these ideas together, Thomson regarded the atom to be a collection of the positive and negative charges held together by electrostatic force. And this model given by the Thomson became famous in the name of the Plum pudding model, which is very similar to the watermelon. So if we cut a watermelon, we will see some black seeds inside. So if we consider these black seeds to be the electrons, then the red flashy mass around this can be regarded as the positive particles. So if this plum pudding model given by the Thomson is true, and if one throws a heavy positively charged particle onto this atom, what should happen? The heavy particle at the high speed should knock out all the light positive and the negative charges inside the atom, and it should travel almost in a straight line undeflected. So keeping this thing in view, Ernest Rutherford, a British physicist, along with his friends Geiger and Marsden, planned to bombard an atom with a heavy positively charged particle, and for this they choose this alpha particle, which comes out from the radioactive element. As you all know that the radioactive elements like thorium, palladium, uranium are highly energetic particles which, in order to become stable, emit different kinds of the radiations like alpha, beta, and gamma. So with this plan in mind, Rutherford and team designed one experiment which looks something like this. So here the glowy stuff, what you can see over here, this is the radioactive element which is actually emitting the positively charged and heavy alpha particles, and those alpha particles are allowed to pass through some narrow slits or narrow openings, and eventually they are allowed to fall on a gold thin ultra thin gold foil having a dimension of 0.004 millimeter. So how much thin is this? To understand this, what you can do, you can take a scale and draw a 1 millimeter long line, and then you can try to divide it into 10,000 equal parts, and one part among these 10,000 parts will be equal to the width of this gold foil. And the screen, what you can see around this gold foil is a fluorescent screen. What does it do? Whenever one alpha particle will make some impact with this fluorescent screen, then one can see some glow on this, or glow or some fluorescence on the screen, and that is how the scattering of the alpha particle could be detected. So this experiment was tried in the year of 1911, and it is famously and popular as a gold foil experiment. So in this experiment, Rutherford expected that if the Thomson's plum pudding model is a correct one, then the heavy alpha particle in its journey through the gold foil will knock out all the light positive and negative charges and will travel almost in a straight line undeflected. But what did they see in reality? In reality, they found that most of the alpha particles passed through the gold foil as they expected, but at the same times few spots could be found here, here and here as well. That means that few of the alpha particles got deflected at small angles and at large angles, and very few of them, almost one among 20,000 particles, rebounded. That means it deflected almost at an angle of 180 degrees. Now why this is so? To understand this, let us have a look into another simpler model. Suppose this is a cotton ball, a large cotton ball, but at the center you can find a red spot. Suppose this is a very tiny ball. It's made up of steel and it is so hard that it can neither be destroyed nor be dislodged by a high-speed bullet. Now if one starts shooting at this cotton ball, then what could be find? One can find that almost all the bullets are passing through that large cotton ball. But when the bullet will make some impact on the will hit this tiny and hard part, it will be deflected either at a very small angle or it will be rebounded like this. So now let us get back to the original experiment. So this was the what could be found in case of the cotton ball. Exactly this kind of the observation was made by the Rutherford. He saw, just I am repeating, that most of the alpha particles passed in a straight line. So one may expect that while traveling the gold foil, the alpha particles didn't hit any hard and heavy object. So it means the maximum part inside an atom is mostly empty. But as it was also observed that few of the alpha particles was deflected either in the small angle or at the large angle. That means somewhere inside the atom there remains a heavy and hard part which cannot be deflected by the heavy alpha particles. Just like the steel ball which was hidden inside the cotton ball, which is causing the deflection of the alpha particle. And this tiny and heavy part inside the atom should be positive. And why is that so? Because had it been negatively charged, it would catch the positively charged alpha particle, and the arrested alpha particle couldn't come out of the gold foil and make fluorescent spot on the screen. Considering all these facts, Rutherford assumed that somewhere inside the atom all the positive charges are compactly packed at a very tiny and small space, making it heavy and highly dense. Rutherford defined this heavy central part as an atom, and he termed this central part of the atom to be the nucleus, and further assumed that the negatively charged electrons are rotating around this nucleus just like our planet Earth revolves around the sun. So in this way the Plum pudding model given by the Thomson was discarded by this new atomic model given by the Rutherford. However, although this Rutherford's new atomic model was very successful in explaining the gold foil experiment, but the Rutherford's atomic model was not also free from errors and disputes. So now let us see that what limitations was there in the Rutherford's gold foil experiment. Now, according to Rutherford's atomic theory, the negatively charged electron that rotates around the nucleus. But if this is true, according to classical electrodynamics theory, when one charged particle rotates in a circular path, it should emit energy. Now, since this electron is losing energy continuously, it cannot rotate in this bigger circle. Rather, it will come closer and closer to the nucleus following this spiral path and ultimately will fall on the nucleus. And if this happens, that means if one negatively charged electron falls on a positively charged nucleus, this should cause the destruction or annihilation of the atom. That means the atom should not exist at all. But we all know that this is not actually the reality. The atoms are very stable, and the matters which are made of these atoms are very stable, and that is why we can see all the matters around us. So this was the first limitation in the Rutherford's model, that it could not explain the stability of an atom. Secondly, if the electron emits a continuous radiation, and if we make some arrangement to record this emission of the radiation in a screen, then we should get a continuous color band. Why is that so? Because as we have discussed, this electron is continuously emitting the radiation, and this rotating electron will gradually decrease its energy along the spiral path. So this electron will emit the radiation of variable energy with variable colors. So as a result, we should get this kind of the continuous multicolor band. But can we find this thing in reality? When one hydrogen gas is exposed to a very high electric field, then only it emits radiation. But that radiation doesn't give this kind of the continuous multicolor band, rather create this kind of the discrete lines on the recorder. So what does it mean? It means that an atom may emit radiation at some particular condition, but the emitted radiation will not take place continuously like this. Rather, it will take place in a discrete manner like this. So this was the second limitation in the Rutherford's atomic model, that it couldn't explain the discrete nature of the hydrogen line spectrum. So there must be some error in the Rutherford's atomic model. Niels Bohr, another eminent scientist from Denmark, could find out the error in the Rutherford's atomic model and proposed a new atomic model in 1913, and that model we'll be discussing in the next class. So I would request you all to go through the textbook and different online contents which has been discussed on this topic, and make yourself prepared about this atomic structure. So for now, so let's stop here and have a good day ahead.